In this video, we're going to be doing a uniform motion problem, and we call these types of problems uniform motion problems because the two objects that are moving, or the two people that are moving, move in the same way, and most commonly this means that they travel the same distance. So in this particular problem, we're told that Arnold and Kay make the same trip, but they do it on different days. So for example, Arnold makes the trip on Tuesday, Kay makes the trip on Thursday. The reason that they tell you they're making the same trip is to let you know that they travel the same amount of distance. So Arnold traveled at 12 miles an hour, Kay traveled at 20 miles an hour, so the trip took her 2 hours less than it took Arnold, which makes sense because if Kay traveled at a faster speed, then the trip is going to take her less time. How far did they travel? So what was the distance that they traveled? Well, to solve a uniform motion problem, the first thing we want to remember is that we're going to be using this equation here for distance, which tells us that distance is equal to rate times time. So if I multiply together the rate that I travel and the amount of time I travel, then I'm going to get the amount of distance that I travel. So this is going to be the formula that we're going to use. The first thing we want to do then is draw a diagram of our motion. So we're going to say both Arnold and Kay started at the same point. So we're going to say that they started here and that they traveled to this point here. So we'll go ahead and say that Arnold started here and he traveled to this point, and so we can call this Arnold's distance. So we'll say the distance of Arnold, d sub a, and then we'll say that Kay started at the same point. She made the same trip, so she started at the same point, she traveled to the same point, and so this is going to be Kay's distance, or d sub k. Because they made the same trip and we know that they traveled the same distance, we can go ahead and say that d sub a, Arnold's distance, is going to be equal to d sub k, Kay's distance. Now we know that distance is equal to rate times time. So when you look at this formula, what we want to realize is that we can make a substitution, right? We know that d is equal to RT, so we can use these interchangeably. So instead of saying distance, we can say rate times time. So we can say Arnold's rate, R sub A, times Arnold's time, T sub A, is going to be equal to K's rate times K's time. So K's rate times K's time. We just substituted rate times time for distance. Since we know that their distances are equal, we know that the product of their rates and times are also going to be equal. The reason we wanted to get to this point is because the only information we've been given in this problem is about Arnold and Kay's rate and time. We haven't been given any information about their distance. That's the unknown that we need to find. So we wanted to get the equation in this form so that we could start plugging in some of the values we've been given. So let's write down what we know, what we've been told in the problem. It says Arnold traveled at a rate of 12 miles an hour. So that's going to be Arnold's rate. So we can go ahead and say Arnold's rate, or R sub A, is going to be equal to 12. We've been told Kay traveled at 20 miles per hour. So that's going to be Kay's rate. So we can say Kay's rate, or R sub K, is going to be equal to 20. Then it tells us the trip took Kay 2 hours less than it took Arnold because she traveled faster. So we can say that Kay's time, or T sub K, Kay's time, is going to be equal to Arnold's time, so T sub A, minus 2. And that should make sense to us because if we think about this, if we say, let's just pretend for a second, that the trip took Arnold 10 hours, then we can say T sub A is 10, we get 10 minus 2, and we can say Kay's time is 8. So if Arnold's time were 10, then Kay's time would be 8, and that would make sense because we know that it took Kay 2 hours less than it took Arnold, and 8 is 2 less than 10. So we know we've written an accurate equation here that relates Kay's time to Arnold's time. So now with these three pieces of information, we can go ahead and plug into this rate times time equation here. We know R sub A is equal to 12, so we'll go ahead and plug that in. We don't have a value yet for T sub A, so we'll go ahead and leave that as is. We know R sub K is equal to 20, K's rate is 20, and we know T sub K, K's time, is equal to T sub A minus 2, so T sub A minus 2. Now we want to go ahead and simplify and solve for T sub A, which is the only variable we have remaining. So we'll get 12 times T sub A is equal to 20 times T sub A minus 40. We just distributed this 20 across the T sub A and then negative 2. Now if we subtract 20 T sub A from both sides, we're going to get negative 8 T sub A is equal to negative 40. Dividing both sides by negative 8, we'll get T sub A is equal to positive 5. which tells us that the amount of time it took Arnold was 5 hours. And we can go ahead and plug Arnold's time into this equation we have for t sub k to get a value for t sub k. So when we do that, we're going to get t sub k is equal to, plugging in 5 for t sub a, we get 5 minus 2. T sub k is equal to 3. Now, since we know that distance is equal to rate times time, and we have the rate and the time for both Arnold and K, we can find the distance that they traveled. So we know that Arnold's rate was 12, and we know that Arnold's time was 5, so his distance is going to be 12 times 5, which we see is 60. K's rate was 20, and K's time was 3, so K's distance will be 20 times 3, which is 60. And this should make sense to us because you can see that we got the same distance for both Arnold and K, and we know that they traveled the same distance because they made the same trip. So we should have gotten equal distances for both Arnold and K, and we can say that they both traveled a distance of 60 miles.